Welcome to day 29, Static versus Dynamic Scoping. In this session, we will explore the rules of scoping, compare static and dynamic scoping, and dive into real-world examples in programming languages. Let's start by understanding what scoping is. Scope defines the region in a program where a variable can be accessed. It governs the visibility and lifetime of variables, helping avoid naming conflicts in the code. Understanding scoping is crucial for writing clean and maintainable code. Now let's look at the two primary types of scoping, static and dynamic. In static scoping, the scope is determined by the structure of the source code and is resolved at compile time. In dynamic scoping, however, the scope is determined at runtime based on the execution call stack. Both approaches have their pros and cons, which we will discuss next. Static scoping, also known as lexical scoping, determines variable binding based on the program's source code structure. This means that when a variable is referenced, the compiler will resolve it by looking at the position of that variable in the code. Let's look at an example from C. Here we define a global variable x and a local variable x within function 1. The local variable shadows the global one within function 1, but outside of it, the global variable x is used. On the other hand, dynamic scoping determines variable binding based on the execution call stack at runtime. This means the value of a variable is resolved based on which function is currently executing. For instance, in libs, the variable x takes the value defined in the most recent function in the call stack, making it dynamic. This can sometimes result in unpredictable behavior, but it offers flexibility in certain use cases. Now let's compare static and dynamic scoping. In static scoping, the variable binding is resolved at compile time, making it easier to predict and debug. Static scoping is more commonly used in modern programming languages. On the other hand, dynamic scoping resolves variable binding at runtime, which can lead to unexpected results and harder debugging. Dynamic scoping offers flexibility but requires more careful management. Most modern programming languages such as C, C++, Python, Java, and JavaScript use static scoping due to its predictability and ease of use. However, languages like libs and Perl allow for scoping, providing more flexibility, especially in specific scenarios. Understanding the scoping rules of the language you are working with is essential for writing effective code. Scoping plays a significant role in debugging, performance, and readability. With static scoping, it's easier to track where variables come from and to ensure that their values are predictable. It also allows for better optimizations during compilation. Dynamic scoping can lead to unexpected results, making it harder to debug and optimize the code. It's important to consider the impact of scoping rules when designing your programs. So, when you should use static or dynamic scoping? Static scoping is generally preferred for large, complex systems because it offers predictability, easier debugging, and better performance. Dynamic scoping can be useful in smaller, flexible systems or in specialized languages where you need more dynamic behavior. Each approach has its place depending on the specific needs of the project. To summarize, static and dynamic scoping are two different ways of managing variable binding in programming languages. Static scoping is more common and predictable, making it easier to understand and debug. Dynamic scoping, while more flexible, can sometimes lead to unexpected behaviors, which can complicate debugging. Choosing the right scoping model depends on your project requirements and the language you are using. Welcome to day 30 of our programming course. In today's session, we will be exploring paradigm-specific language constructs, focusing on how different programming paradigms introduce unique constructs that help developers solve problems in various ways. Programming paradigms introduce specific contrasts that shape how developers approach coding challenges. Each paradigm brings its own set of tools and techniques for solving problems, making it essential to understand these contrasts in order to choose the best approach for a given task. Let's start with functional programming. One of its key features is first-class functions, where functions are treated as first-class citizens. This allows us to pass functions as arguments, return them from other functions, and assign them to variables. Another important construct is map and reduce, which allows us to operate on collections of data. We also have lazy evaluation, where expressions are evaluated only when needed, and pure functions, which are functions that have no side effects and always return the same output for the same input. First-class functions allow us to pass functions around just like any other variable. For example, in Haskell, we can define an add function and then pass this function to another function that applies it to a list of numbers. This makes our code modular and more reusable. Map and reduce are higher order functions that are commonly used in functional programming. Map applies a function to each element in a collection, while reduce combines all the elements of a collection into a single value. For instance, in Python, we can use map to double each element in a list and reduce to sum all elements in a list. Lazy evaluation is another powerful concept in functional programming. It means that an expression is not evaluated until its value is needed. This allows us to work with infinite data structures or rely computation or delay computation until absolutely necessary. In Haskell, we can define an infinite list and take only the first few elements without causing any performance issues. Next, let's look at object-oriented programming, OOP. OOP introduces constructs like classes and objects, which acts as blueprints for creating instances of objects. Inheritance allows one class to inherit properties and methods from another, while polymorphism enables different classes to respond to the same method in different ways. Encapsulation protects an object's internal state by only exposing relevant information. In OOP, we define classes that serve as blueprints for creating objects. For example, in Python, we can define a class car with properties like model and methods like drive. We can then create an instance of the class like myCar equals to car Tesla and call its methods like mycar.drive to perform actions. Inheritance allows one class to inherit the functionality of another, while polymorphism lets us use the same method name for different types of objects. For instance, we might have a shape class with a method area and then circle and square classes that implements the area method in their own way. Polymorphism allows us to call area on both objects even though their implementations are different. Logic programming is based on facts and rules. It defines relationships between different entities and allows us to make logical deductions. For example, in Prolog, We define facts like parent Alice, Bob, and then use rules to deduce relationships like ancestors X, Y, parent X, Y, which means that X is an ancestor of Y if X is a parent of Y. Concurrent programming deals with multiple tasks running in parallel. Key constructs include threads, which are independent execution units, and synchronization primitives like locks and semaphores to manage concurrent access to shared resources. Message passing allows processes to communicate with each other, as seen in languages like Erlang. In concurrent programming, we use threads to execute tasks independently. For instance, in Python, we can create a thread to print numbers concurrently with other tasks. Synchronization primitives like locks are used to ensure that threads do not interfere with each other when accessing shared data. Message passing is another critical feature in concurrent programming. It enables processes to communicate with each other by sending messages. For example, in Erlang, we can send messages between processes to coordinate their actions. This approach is especially useful in distributed systems. In conclusion, each programming paradigm offers specific contrasts that shape how we write and structure code. By understanding these constructs, such as first-class functions in functional programming, inheritance in OOP, and message passing in concurrent programming, we can make better decisions when choosing the right paradigm and tools for a task. Thank you for your attention. I would now like to open the floor for any questions or further discussions on paradigm-specific language constructs. Feel free to share your thoughts or ask for clarification on any topic we covered today. Welcome to the presentation on software design and language impact. Today we will explore how different programming languages influence software design, architecture, and overall development. In software development, the choice of programming language plays a significant role in shaping the design and functionality of a system. For example, languages with static typing such as Java or C++ encourage well-defined architecture and help catch errors at compile time. On the other hand, dynamic typing languages like Python and Ruby prioritize flexibility and fast development, but at the cost of potentially more runtime errors. Similarly, languages like C and C++ offer manual memory management, giving developers greater control, whereas languages like Java or Python handle memory management automatically through garbage collections, simplifying development but adding some performance overhead. When it comes to concurrency, languages like Go and Rust have built-in support for handling multiple tasks simultaneously, while others like Python rely on external libraries to manage concurrency. Different languages of software have different needs, and language choice is critical. For system software like operating systems and device drivers, languages like C and C++ are preferred due to their low level capabilities and control over hardware. For enterprise applications that require scalability and robustness, Java is a popular choice due to its portability and strong typing. When it comes to web development, JavaScript dominates the front end, and with Node.js it also powers the backend. Python and Ruby are also widely used for web applications due to their simplicity and extensive frameworks. In data science and machine learning, Python has become the go-to language because of its rich ecosystem of libraries like TensorFlow and Pandas. For embedded systems where performance and direct hardware interaction are crucial, C and C++ continue to be the dominant choices. Design patterns, which are reusable solutions to common design problems, are influenced by the features of the programming language. Object-oriented languages like Java, C++, and Python encourage patterns like singleton, factory, and observer thanks to their support for classes, inheritance, and polymorphism. In functional programming languages like Haskell or Lisp, patterns like MapReduce are more prevalent as these languages emphasize immutability and the use of higher order functions. Modern concurrency languages like Go make use of patterns like the Ocar pool and publisher subscriber to manage multiple tasks concurrently using lightweight Go routines and channels. Object-oriented programming languages are built around the concepts of objects, classes, inheritance, and polymorphism. One common design pattern in OOP is the factory pattern, which is used to create objects in a flexible manner without specifying the exact class of the object to be created. This is particularly useful in Java, where object creation is often abstracted through interfaces and factory methods to promote loose coupling and easier testing. Functional programming focuses on immutability and the use of pure functions. The MapReduce pattern, popularized in languages like Haskell, Lisp, and Python, is a prime example of functional programming in action. It involves applying a function to each element of a collection, then reducing the result to a single value, such as the sum or average. This pattern is particularly effective in processing large datasets in parallel, which is why it is commonly used in distributed systems like Hadoop. Concurrency is a key consideration in modern software design, especially in high-performance systems. Languages like Go have built-in concurrency support through Go routines and channels, making it easy to implement patterns like publisher subscriber and worker pool. These patterns allow multiple tasks to be performed in parallel, improving the efficiency and responsiveness of applications, especially in systems handling many simultaneous connections such as web servers. Maintaining and extending software systems requires careful consideration of the language features. Readable and modular languages like Python make it easier to manage and update code over time. With strong community support and well-documented libraries, developers can easily extend functionality without breaking existing features. Flexible languages like Python and Ruby also allow easy integration of new modules or third-party libraries, making them ideal for rapidly evolving projects. When selecting a programming language, developers must weigh performance against productivity. High-performance languages like C and C++ provide fine-grained control over memory and processing but require more effort to handle memory management and concurrency. In contrast, languages like Python and Ruby emphasize rapid development, allowing developers to quickly prototype and iterate through though a potential sacrifice in performance. Additionally, long-term maintainability should be considered, with languages like Java and C# offering strong ecosystem support for enterprise applications, and Rust providing long-term safety for system-level development. To summarize, the choice of programming language profoundly affects software design, maintenance, and extensibility. By understanding the strengths and limitations of various languages, developers can make informed decisions that ensure the success of their projects. Thank you for your time and feel free to reach out if you have any questions or need further clarifications. Welcome to day 32 of our course, where we explore the advanced features of modern programming languages. Today we will be discussing coroutines, async await, metaprogramming, reflection, and introspection, some of the most powerful tools available in modern languages to enhance performance, readability, and flexibility in your code. Let's start with coroutines, async await, and concurrency. Coroutines allow functions to pause and resume execution without blocking threads. This is especially useful for tasks like I/O operations, networking, or event-driven programming. In languages like Python, Kotlin, C Sharp, and JavaScript, coroutines help manage asynchronous tasks without needing to deal with complicated callback mechanisms. Async await is a feature that simplifies asynchronous programming. It makes the code more readable and avoids the complexity of callbacks by allowing developers to write asynchronous code in a synchronous manner. And when we talk about concurrency, we are referring to the ability to execute multiple tasks simultaneously. This allows for more efficient use of system resources and better performance. Go's coroutines and Python's Essentio are great examples of concurrency in action. Concurrency is a key feature of modern programming languages. It involves executing tasks concurrently without blocking the main program execution. While concurrency does not necessarily mean parallel execution, it allows multiple tasks to progress independently, which helps with resource utilization and performance. Languages like Go with its lightweight Go routines and Python with which uses Asyncio for asynchronous tasks provide tools to implement concurrency effectively. It's a critical feature for large-scale applications that require responsiveness and efficient resource management. Now let's dive into metaprogramming. This is a powerful feature where the code can manipulate other code at runtime or even generate new code. There are two main types of metaprogramming: compile time and runtime. At compile time, metaprogramming allows for the creation of templates or generic code. For example, in C++, templates lets you write code that works for any data type. At runtime, languages like Python and Ruby allow for more dynamic code manipulation, such as creating new classes or methods. The key benefit of metaprogramming is the increased flexibility it provides. It can write less boilerplate code and make your programs more adaptable. Metaprogramming is widely used in frameworks and libraries to adapt code dynamically based on the user's need. For instance, in Ruby on Rails, metaprogramming is used to build domain-specific languages (DSLs), which are mini languages for specific tasks, making the code cleaner and more readable. Another application of metaprogramming is in code generation, where parts of the program can be created dynamically based on the environment or user inputs. This reduces the need for repetitive code, making the development process more efficient. Let's move on to reflection and introspection. Reflection is the ability of a program to inspect and modify its own structure at runtime. It allows developers to dynamically load classes, methods, and attributes. Introspection, a related concept, focuses on examining the properties of an object. For example, in Python, the dir function can be used to inspect an object's attributes and methods. These features are often used in frameworks that need to adjust their behavior dynamically based on the objects they are working with. Next, we have type interference, which allows programming languages to automatically deduce the type of a variable based on its assigned value. Languages like Kotlin, TypeScript, and Rust all use type inference to make the code cleaner and less verbose. For example, Kotlin allows you to declare a variable without specifying its type, and it will infer the correct type based on the assigned value. This not only reduces redundancy but also improves code readability. Pattern matching is another advanced feature that allows you to match values against patterns or types. It makes conditional logic more expensive and readable. In languages like Python, JavaScript, and Scala, pattern matching provides a more intuitive way to handle complex conditions. For instance, Python's match statement, introduced in version 3.10, allows you to match variables against patterns directly, making code much more elegant compared to traditional if-else or switch statements. Let's talk about memory management, particularly in languages like Rust. Rust is known for its unique approach to memory management, which does not rely on garbage collection. Instead, it uses ownership, borrowing, and lifetimes to ensure memory safety at compile time. This approach prevents common issues like memory leaks and race conditions, ensuring that developers can write high performance applications without worrying about manual memory management. However, it does require more careful programming, making it more challenging for developers new to the language. With these advanced features like coroutines, metaprogramming, and memory management offer significant benefits that are trade-offs. The primary advantage is that these features allow for more efficient, flexible, and readable code. However, they can also increase complexity and introduce performance overhead, such as with reflection or dynamic typing. Moreover, some of these features, like Rust's memory management model, have a steeper learning curve. Developers need to balance the use of these features based on the specific requirements of their projects. In conclusion, modern programming languages provide a wide array of advanced features that can drastically improve the quality and performance of your code. From coroutines and async/await for concurrency to metaprogramming and reflection for dynamic behavior, these tools give developers a high degree of flexibility and control over their programs. Mastering these features will enable you to write more efficient, scalable, and maintainable software. However, it's important to understand when and how to use them to avoid overcomplicating your code. Thank you for joining me today. I hope you have a deeper understanding of advanced programming features like coroutines, metaprogrammings, and reflection. If you have any questions or would like to dive deeper into any topic, feel free to reach out. See you in the next session. Welcome to today's presentation on optimization techniques in programming languages. We will explore the key strategies for improving memory usage, performance, and the role of compiler optimizations in various programming languages. Let's dive into this Crucial techniques. Optimization is an essential aspect of software development. In this section, we will discuss the different types of optimization techniques: memory optimization, performance optimization, and compiler optimizations. Additionally, we will look at language-specific optimization strategies and the role of profiling and benchmarking in identifying bottlenecks in your code. Code optimization varies across different programming languages. For example, in low-level languages like C and C++, manual memory management can significantly enhance performance. On the other hand, languages like Java rely on just-in-time compilation and automatic garbage collection. Python and JavaScript focus on profiling, list comprehensions, and optimizing asynchronous tasks. Understanding how optimization works in different languages helps you select the best approach for a specific application. Memory optimization is a critical aspect of performance, especially in resource-constrained environments. Different languages provide different memory management techniques. For instance, languages like Java and Python have automatic garbage collection, while C and C++ require manual memory management. Optimizing memory usage can include practices like reusing objects, using memory pools, and employing data compression techniques. Performance optimization involves improving the efficiency of your code by reducing time and space complexity. General optimization strategies include loop optimization, reducing redundant calculations, and optimizing algorithms. Machine level optimizations focus on using platform specific features, while cache optimization improves data retrieval speeds by leveraging the system's cache memory effectively. Concurrency and parallelism are vital techniques for optimizing performance in multi-threaded applications. By dividing tasks into smaller, independent units, you can execute them concurrently to speed up processing. Handling synchronization and avoiding deadlocks are crucial challenges in parallelism. Optimizing concurrency models helps achieve better performance and scalability in modern applications. Compilers play a significant role in performance optimization. Various techniques such as constant propagation, loop unrolling, and inlining can be applied by the compiler to improve execution speed. Optimizations like vectorization and using SIMD, single instruction multiple data, enhance performance on multi-core processors. Compilers also offer different optimization levels such as O1, O2, or O3, allowing developers to balance between compilation time and execution speed. Profiling and benchmarking are critical tools for identifying performance bottlenecks. Profiling tools like gprof, visualvm, and cprofile allow you to analyze the runtime behavior of your application. Benchmarking tools such as time and benchmark.js help you measure execution time, scalability, and resource usage. By identifying performance bottlenecks, you can focus on your optimization efforts where they matter the most. Choosing the right data structure can greatly impact performance. For instance, using a hash table instead of a list allows for faster lookups. It's important to understand the trade-offs between different data structures like arrays, linked lists, and trees, and select the one that best fits the problem you are solving. Efficient data structures can reduce both memory usage and processing time. In real-world applications, optimization techniques have a profound impact. For example, search algorithms like binary search outperform linear search in sorted datasets. Database query optimization through indexing and query planning improves performance in large datasets. In web development, optimizing the DOM using lazy loading and implementing caching strategies can significantly improve the speed and responsiveness of your web application. To summarize, optimization is crucial for enhancing the performance and efficiency of your software. Whether it's through memory optimization, performance tuning, or leveraging compiler optimizations, the right techniques can help make a significant difference. Don't forget the importance of profiling and benchmarking in identifying areas to optimize and refine. Thank you for your attention. We have covered several topics on optimization techniques across different programming languages. Now I would be happy to answer any questions or discuss specific optimization challenges you have encountered in your own projects. Welcome to today's presentation on language evaluation. In this session, we will dive into the criteria for assessing programming languages, explore evaluation methods, and discuss real-world studies. I am excited to guide you through this topic. Here's a quick look at our agenda. We will begin by discussing the criteria for evaluating programming languages. Then we will move on to the evaluation methods and metrics, followed by real-world case studies. We will also look at industry adoption and practical considerations before wrapping up the challenges in language evaluation. Let's start by looking at the criteria for evaluating programming languages. We consider factors like readability, which focuses on syntax and clarity, and reliability, which involves things like type systems and error handling. Efficiency looks at performance and optimization, while maintainability emphasizes modularity and long-term support. Next, we discuss the methods and metrics used for evaluation. Theoretical approaches involve formal semantics and grammar, while practical approaches rely on performance benchmarking tools and developer feedback. Both perspectives are crucial when assessing the effectiveness of a language. Now let's examine some real-world case studies. Rust versus C++ demonstrates how Rust focuses on memory safety while C++ offers low-level control. JavaScript versus TypeScript shows how static typing in TypeScript enhances development workflows, and Python versus Java highlights simplicity versus scalability in language design. Industry adoption plays a significant role in the evolution of programming languages. A language ecosystem, including its frameworks, libraries, and community support, can determine its success. For example, Python's extensive ecosystem in machine learning, with libraries like TensorFlow and Pandas, has greatly contributed to its popularity. Evaluating ecosystem factors is also essential. A language ecosystem influences its adoption. Strong ecosystems provide developer tools, libraries, and active community support, which in turn drive a language's success and longevity in the industry. However, language evaluation does come with challenges. For one, there's the risk of bias due to developers' personal experiences with certain languages. Readability can also be subjective, as different developers have different preferences. Additionally, there are no universal benchmarks that apply to all languages and use cases. By the end of this session, you should be able to understand the factors that affect the effectiveness of a programming language, use both theoretical and practical evaluation methods, critically compare languages based on various factors, and discuss the long-term impacts of language design choices. For your homework or project, I recommend a comparative evaluation project. Choose two programming languages, evaluate them based on their readability, reliability, efficiency, and maintainability, and present your findings with real-world use cases examples. In conclusion, we have covered the essential aspects of language evaluation, including the criteria, methods, use cases, case studies, and practical considerations. It's clear that evaluating programming languages is a multi-phased task, and understanding these factors will help you make more informed decisions when choosing a language. Thank you for your attention. Now, I would like to open the floor for any questions you may have. Please feel free to ask anything related to the topics we have covered today. Hello and welcome to this presentation on trends in programming languages. Today we will explore the evolving landscape of programming languages, modern trends, the rise of new languages like Rust and Go, and the impact of AI on language design. As we dive into the trends, we will first cover the key areas influencing the world of programming languages. Modern trends include the rise of functional, declarative, and hybrid programming paradigms. We will also discuss new languages like Rust and Go and examine how AI is reshaping the way languages are designed and optimized. Functional programming has gained significant traction in recent years. With its core principles of immutability and pure functions, functional programming like Haskell, Scala, and F Sharp help reduce side effects, making concurrency easier to manage. Languages like Python have also adopted functional features, making functional programming more accessible to a broader audience. On the other hand, declarative programming focuses on what you want to achieve rather than how to do it. This leads to simpler, more readable code. Languages like SQL, HTML, and C++ excel in declarative programming, where the programmer declares the logic without specifying control flow. This approach is widely used in cloud computing, APIs, and web development. Hybrid programming languages are increasingly popular. These languages combine multiple paradigms, giving developers the flexibility to choose the best approach for the task at hand. For example, Python supports functional programming constructs, while Java has adopted lambda expressions from functional programming. Rust, a language designed for system-level programming, is making waves due to its focus on memory safety and performance. Rust's unique ownership system eliminates data races at compile time, offering significant advantages for concurrent programming. It ideal for it's ideal for use cases like WebAssembly, game development, and low-level system design. Go, developed by Google, is another rising star. With its simplicity and speed, Go excels in handling concurrency with its core routines. It's ideal for cloud computing, microservices, and network applications. Go's design emphasizes ease of use and efficient resource management, making it a popular choice for modern infrastructures. AI is starting to play a crucial role in programming language design. From AI-driven code optimization to the development of new paradigms, AI is enhancing language features and improving compilers. As machine learning and AI technologies evolve, we can expect even more innovations in the design and implementation of programming languages. Machine learning and AI are transforming the way we write and optimize code. Tools like auto-completion, intelligent debugging assistance, and code generation are powered by machine learning. These tools make developers more work more efficient, and the future we may see even more sophisticated AI-driven programming environments. Domain-specific languages or DSLs are tailored for specific industries or problem domains. By providing highly specialized syntax and semantics, DSLs simplify coding tasks. Examples include TensorFlow for machine learning, R for statistical computing, and SQL for database queries. DSL improve productivity and allow developers to focus on problem, not the language. An interesting trend is the integration of low-level features in high-level languages. For example, RAS memory management system gives developers fine-grained control over memory without sacrificing the productivity of a high-level language. This combination of low-level control with high-level abstraction is becoming a powerful tool for modern software development. Finally, there's a growing emphasis on code readability and maintainability. Modern programming languages are designed to be clear, simple, and easy to understand. Tools that enforce code style, along with features like clear syntax and powerful IDEs, help developers maintain cleaner, more efficient code bases. In summary, programming languages are constantly evolving. We see a rise in functional and declarative programming, with languages like Rust and Go leading the charge. AI is significantly sharpening language design, and DSLs are streamlining domain specific tasks. Additionally, the integration of low level features in high level languages is giving developers more control without compromising productivity. To conclude, the future of programming languages looks exciting with AI driven evolution, hybrid paradigms, and powerful new tools paving the way forward. Staying updated with these trends will be essential for any developer looking to stay ahead in the ever evolving world of programming. Thank you for listening and feel free to reach out with any questions.